Hello everyone, and welcome back to another lecture video. In this lecture video, we're going to be covering momentum balance. Now, it sounds crazy, and if I'm going to be honest, it is a little crazy, but momentum balance actually leads to two of the most critical things in continuum or solid mechanics, or maybe not perhaps the most critical, but things that'll make our lives a lot easier. All right, so let's get started. It all begins with Newton and Euler. Our good friends Newton and Euler, they derived a lot of the stuff that we use in engineering, and for here in solid mechanics, it's not really an exception. So it all starts with Newton. Newton's second law of motion states that the rate of change of the linear momentum of an object with respect to time is equal to the net force acting on that object. And you guys are saying, hold on one second, Clayton. I remember Newton's law of motion, but I don't remember it quite sounding like that. So let's go over it and see if we can perhaps make it a bit more familiar to you guys. So we know that the sum of the forces is actually the derivative of the linear momentum, which is just m times v, with respect to time. And you guys are going to say, well, that doesn't look very familiar. Well, it will, because typically our mass is constant. And if we take the derivative of something constant, well, nothing really happens. So we can bring it outside. So therefore, the sum of the force is equal to mass times the change in velocity with respect to time. And we say, oh, hold on a second, change in velocity with respect to time, that's equal to acceleration. So now perhaps the equation is a little bit more familiar, where the sum of the forces acting on an object is equal to the mass of the object times acceleration. So that's what Newton did. Then Euler comes along and says, you know what? I'm going to be super smart and introduce two laws to apply to a continuum. The first one is balance of linear momentum, which is as follows. And I'm not going to try and say it, I'll mess up and sound like an idiot. So there it is. You guys have already seen all the components, such as the traction vector, the body force vector, etc., etc. And then he also introduced a second one, which is the balance of angular momentum. Again, not going to try and say it because I'll sound like an idiot. But basically, this is going to be the topic of this lecture. Those two balances of momentum. The first one being linear momentum, and the second one being angular momentum. So if you guys are new to this and you're looking at these equations, you're thinking, holy shit, this looks absolutely terrible. I don't even know where to start with these. I don't even know what they mean, but that's okay. These are the kind of like the Wikipedia equations. You guys ever go on Wikipedia to try and search for something and it just makes you feel really dumb, you don't really understand? Well, that's what these equations basically do. They're very hard to understand, but if we take an in-depth look at them, hopefully they become a little bit more clear. So what we're going to do is start with the balance of linear momentum. How do we do that? Well, we're going to go back to our old friend, the potato, and we're going to take an infinitesimal cube of the potato. I call this the potato continuum, if you will. Now, as we talked about in the last lecture, even the one before that, I'm not sure which one it is, but when we talked about the Cauchy stress tensor, basically said that each face of this cube is going to have three stress components. Those three stress components being the components of what we call the traction vector. So if I were to take this cube, take it outside of the potato, I know that each face of this cube is going to have three stress components. Now, the stress components, and we didn't talk about this last time, is they actually change over the face of the cube, and it makes sense. If I were to look at one point in a body, it's going to have some stresses, but if I were to look at a point, let's say at a distance away from the other point, the stresses are going to change. So what we do is we model this through a simplified Taylor series expansion, where we say on one side of the cube we have the stresses, say sigma 1, 1, and the other side of the cube we have sigma 1, 1 plus the change in sigma 1, 1 over the length of that cube. So that's how we're going to model the stress, the change of stress throughout the side of the cube. Now, in addition to those traction vectors that we have on each face of the cube, we also have body forces acting on the cube. And when you look at body forces, they always look really confusing. But essentially, this would be something like gravity. So if you guys are thinking of a real life scenario, the body forces we typically consider are that rho b2, or the gravity in the vertical direction. We don't really have gravity forces in the horizontal direction, so therefore typically rho b1 and rho b3 are going to be equal to 0. But for purposes of deriving things, it is important to include them because for some applications, for instance, magnetics, they will have those forces in the horizontal direction. So it is important to kind of keep that in mind. All right, so with this kind of methodology, we can move on to the balance of linear momentum. And what we're going to do is we're going to take that same cube, but to make it simple or make it more simple or simplified, we're only going to consider the forces in the E1 direction. So I'm going to take my potato, going to take my cube out, and I'm just going to label all of my forces in the horizontal direction. So the one we've already talked about, On one side, we have sigma 1, 1, and on the other side, we have sigma 1, 1 plus the change in sigma 1, 1 over that distance, delta x1. All right. We also said that we have a body force in the horizontal direction, which is rho b1, but we also know that we have other stress components coming from the other faces of the cube. So if we were to look at the top face of the cube, we know that we have a stress component sigma 2, 1, and then on the other side, we have sigma 2, 1 plus the change in sigma 2, 1 over the distance delta x2, or the distance in the E2 direction. And finally, on that face of the cube that's closest to the screen, and I use that in quotation marks because of course this is all 2D, but I tried my best to make it 3D, we have another stress component, sigma 3, 1, and then on the other side we have sigma 3, 1 plus the change in sigma 3, 1 over the length delta x3, or the distance in that E3 direction, right? So we only considered the horizontal forces, and what we're going to do with this is we're going to actually take the summation of the forces in the E1 direction, or the horizontal direction. And the reason why I don't say horizontal direction is because technically that E3 is in the horizontal direction as well. It makes things really confusing. So I'm taking the sum of the forces in the E1 direction, and I get the following equation. Now, when professors usually give you these long equations and they say, oh, it's just obtained from the figure, it can be kind of hard to see where things come from. So let's just go over real quick just to make sure we're all on the same page. The first component, negative sigma 1, 1 times delta x2 times delta x3, well, that just comes from our sigma 1, 1 component. Now, the reason why we have that delta x2 and delta x3 is because we're taking some of the forces. We're not taking some of the stresses. So all we're doing is we're taking the stress on that face and multiplying it by the area of that face. All right, so nice and easy. Then we move on to sigma 3, 1. So that's that force kind of on the back side of the cube. We can see it's going to the left, so we have the negative component. And of course, we multiply it by the corresponding area of that face. All right, moving on from there, we got sigma 2, 1 times delta x1, delta x3. Again, pretty self-explanatory, not too bad thus far. And then we just move on to the other side. So on the other side, we have sigma 2, 1 plus the change in sigma 2, 1 over the length delta x2, and then times that by its corresponding area. And we move on with sigma 1, 1 there, sigma 3, 1 down there. And then finally, we have to also include that body force vector. So the key to keep in mind is when we're taking the forces, some of the forces, we want forces. It makes sense, right? Some of the forces, we want forces. So when we're dealing with stress, we must multiply by an area. But when we're dealing with body forces, we actually have to multiply by a volume. All right, so that's why we have a delta x1, delta x2, delta x3 there. And this makes sense. If we're dealing with gravity of something, we're dealing with the volume of an object, not specifically just a surface. All right, so we're going to move on a little bit more, and we're going to say, you know what? A lot of these terms appear in a lot of places. Well, there's actually some simplification we can make. That sigma 1, 1 times delta x2, delta x3, well, it actually appears on the other side, so we can cancel it out. And same thing for sigma 2, 1, and the same thing for sigma 3, 1. So just by doing this over here, we actually simplify our equation to the following. All right, so now the question becomes is, what is this equation equal to? Remember, when I'm trying to manipulate equations, I have to have both sides of the equations. Well, because of those nice Newton law of motions, we know that the sum of the forces on something is just going to be the mass times the acceleration. So now that I have an equation and I know both sides, I can start manipulating it to try and get a nice relationship going. All right, and the first thing we're going to look at is that mass term. Just like we did in the Cauchy stress tensor, we're actually going to modify that mass term in terms of density, which is rho, and the volume. Mass is equal to the density times the volume. It makes sense. And we're going to take it a step further. Because since we're dealing with a cube, we know that the volume is simply going to be delta x1 times delta x2 times delta x3. So I'm going to take that new bad boy and I'm going to substitute it into my equation. So again, this is nice because I have an equation. I know both sides of it, therefore I can start doing some mathematic manipulations. And the first thing that's very obvious to see is that delta x1, delta x2, delta x3, or the volume of that cube, it appears in every single term. So we can simply divide both sides by that volume, and we simplify our equation into the following, where the change in sigma 1, 1 with respect to x1, plus the change in sigma 2, 1 with respect to x2, plus the change in sigma 3, 1 with respect to x3, plus rho b1 is equal to rho a1. All right, so this is kind of what we end up with, and this is very important. So what we're going to do is we're going to repeat the same process that we just did, except instead of taking summation of the forces in the E1 direction, we're going to take it in the E2 and the E3 direction. All right, and these are called our equilibrium equations. So if I do it in the E2 direction, sum of the forces is equal to m times A2, I get the following equation. And if I were to do sum of the forces in the E3 direction is equal to m times A3, I get the following equation. Now, I'm not going to say it because I'm going to show you right here. These are our equations of equilibrium. All right, so when you guys dealt with statics, you guys know that the sum of the forces must equal 0, and you basically use those to solve for things in beams. Well, when we're dealing with a continuum and we have our Cauchy state of stress, we use these equations right here to solve for our equilibrium in the continuum. So if you guys are saying, you know what, Clayton, that looks pretty gross, I want it in component form, well, joke's on you, component form actually looks a little bit grosser. And again, if we look at these, it's like the displacement gradient. If you guys remember the displacement gradient, there's a bunch of partial derivatives, but it's actually pretty nice. It's not too bad if we look at it. All we're doing is taking partial derivatives of the stress components with respect to x1, x2, and x3. It's not too bad at all. Now, the key here, and this is what usually gets the undergrad students, but it's not going to get you guys are smarter than that, is that these equilibrium equations must satisfy every point in the continuum. So although it appears like we only have 3 equations to solve for things in our continuum, we actually have 3 equations times every point we're interested in looking at. For instance, if I were to look at, let's say, 6 different points on our continuum, well, then I times those 6 points by 3, because basically I have these 3 equations and they must apply for all 6 points on the continuum. Therefore, I technically, and I use technically in air quotes, of course, we technically have 18 equations, because remember, these 3 equations must satisfy every single point on the continuum. It's a trick that professors love to do where they make you solve for, let's say, 5 variables, and they give you these 3 equations. A lot of students will go, well, I got 3 equations, 5 unknowns, I can't really do anything. But once you realize that every point must be satisfied by these equilibrium equations, you guys will be good to go. All right, so that's going to be the balance of linear momentum. It was a big, ugly equation at the beginning. We simplified it, and what it leads to is our equations of equilibrium for a continuum. So I'd write these down, and remember that small x in the equation there, typically when we're representing these material points, we use big X. So the big X and the small x in this case are interchangeable. The small x here is not referring to position functions or anything like that. It's actually just referring to x1, x2, and x3. Now, the second one that we discussed also is the balance of angular momentum. This looks even grosser than the balance of linear momentum, and it is. But this is perhaps one of the most important ones. What is it used for? Well, it's actually used for the symmetry of the Cauchy stress tensor. So when I showed you guys the Cauchy stress tensor, I just showed it to you, and I said, oh, a nice property of this is it's actually symmetric. Sigma ij is equal to sigma ji. But I didn't prove it. You know, I was very sneaky there. I didn't prove it. I just told you guys what it is, and I told you guys to trust me. Now, what's nice for me is sometimes you guys trust me. I find that the level of trust I have with students widely varies. If I were teaching a first-year statics course, they trust anything I say. I can tell them that the sky is green. They would write it down in their notebooks. They'd be happy. I teach, let's say, third years. They still trust me for the most part, but they often wonder why. So if I were to tell them that it's symmetric, well, some of the students would start going, well, why is it symmetric? And then you teach graduate students. And graduate students, they're a whole different ballgame. They don't trust anything. I tell them that the stress tensor is symmetric. They ask why, and then they follow up with prove it. All right, so what we're going to do now is actually going to prove that the Cauchy stress tensor is symmetric. And again, it's the result of the balance of angular momentum. So the angular momentum, which I put as that fancy L there, what we're basically saying is that the change in angular momentum with respect to t is equal to the summation of the moments, the moments created on that object. So what we're going to do when we start looking at this equation is we're just going to analyze both sides, and then we're going to equate them and see what happens. So let's start with the angular momentum about the E3 axis. So if we're dealing with the E3 axis, basically we're looking at all the forces in the E1, E2 plane. All right, so what we're going to do, angular momentum about the E3 axis, well, we basically get this figure over here. Now, what we do is we put our little square, or material square, whatever you guys want to call it, we put it at a distance away from the origin because, again, we're dealing with moments here. Nothing's going to be directly at the origin. And we're going to say that the centroid of our little plate here is at a distance r1 and r2 away from the origin. So if I'm dealing with angular momentum, it's very simple. I got angular momentum basically, or I got my linear momentum basically going in two directions. So my angular momentum is simply going to be delta m times v2 multiplied by r1 minus delta m times 1 multiplied by r2. Just like before, we realized that we don't really deal with mass components, so we're going to swap that into the density rho times the volume, and that's basically it. And then we're just going to take the derivative with respect to time. Now, it sounds like we're going to do something crazy, but we're not. All I did to this equation was I just added d over dt into, oh sorry, I went a little bit too fast, a little bit premature, if you will. All I did was add a d over dt to the beginning of each one of the components. I didn't actually try and take any derivatives. I just made it sound more fancy than it actually was. So we're going to leave that left-hand side of the equation just as that right there. And as you guys are going to see, it's going to be just fine to leave it like that because stuff will start to cancel. Now, on the other side, we have the summation of the moments. And now, what that is going to be is it's going to be the summation of the moments, or the total moment, due to those stress components, as well as the body forces about the E3 axis. So we're going to go back to our nice figure over here. We know that the centroid is located at a distance r1 and r2 from our origin, and we're just going to add our stresses. So we know that we had sigma 2,1 and sigma 2,1 plus the change in sigma 2,1. On the other side, we had sigma 1,2 times our, and then sigma 1,2 plus the change in sigma 1,2. And then when we're looking at the horizontal direction, it actually gets a lot more messy. We have sigma 1,1, we have sigma 3,1, and then we had rho B1. So basically what happens is each one of these components acted on a different face, as you guys remember. But since I'm trying to simplify this into a 2D schematic, I basically have to include them all kind of going along the same arrow. So it gets a little bit messy. So if you guys remember sigma 1,1, that was the one acting on the face in the E3 direction. And then we had our body forces acting in the horizontal direction. And then we had sigma 3,1 acting on the faces that were in the E1, E2 plane. So this is why there looks like there's more forces than what we had previously. Similarly, we have the same thing in the vertical direction. So if we were to look at those stress components in the vertical direction, we had sigma 2,2, and we also had sigma 3,2. Now, just like the horizontal direction, we also have a body force in the vertical direction, which is rho B2. Now, if you guys are looking at the change in stresses, you guys are saying, well, hold on, Clayton, when you were talking about the change in stresses before, you didn't go delta sigma 1,1, you had the partial derivative of sigma 1,1 with respect to x, etc., etc. Well, that's true. The only reason why I tried to simplify it right here is just to make it easier to write on the same page. If I were to include kind of the full thing here where delta sigma is equal to the partial derivative of sigma with respect to x, then multiplied by the distance, well, I just would have ran out of room. So that's why I tried to simplify it right there, and then I just make a little bit note of what exactly delta sigma is referring to. All right, so as you guys may have guessed, what we're going to do, we're going to take the moment. And this looks disgusting, because if we look at all these stress components, it looks like we have like 15 of them. It's going to get messy. So what happens is you guys get the following equation. And you guys say, hold on, you said it was going to be messy, but that looks nice and easy. Well, this is the equation after the simplification. So if you guys remember the balance of linear momentum, one of the things we were able to do immediately was start canceling out terms. So what you do is you do the summation of the moments, and then after you guys cancel out the terms, then you guys are left with the following equation. If you guys don't cancel out the terms, this equation is like 4 or 5 lines long. It's actually extremely gross. But now we have a nice, again, nice in air quotes because it's not too nice right now, but we have a nice equation for the summation of the moments. All right, so now the goal becomes how can we simplify this? Because of course, if we look at that, it's already really gross. Well, what we're actually going to do is use the balance of linear momentum, or basically we're going to use equilibrium. So we have a nice equilibrium equation, and we said that all the summation of forces in a direction is going to be equal to the mass times the acceleration. Now, remember before we went from linear momentum to mass times acceleration, but now I'm going to actually work backwards. What I'm doing is I'm saying that mass times acceleration, well, that's actually equal to rho times the volume times the velocity, and then take that derivative with respect to time. So I worked a little bit backwards, and you guys will see why. Now, the key here, and the reason why we're using equilibrium equations, is because if we look at what our equilibrium equation is equal to, well, all 4 of those terms actually appear in our summation of the moments. Those are all the ones that are written in red. So what I'm going to do is I'm going to take out all four of those terms, and I'm going to replace it with that time derivative of rho v times velocity. All right, so it's actually works out quite nice and easy for us. And again, what we're going to do is we're going to repeat this with equilibrium equation number 2, because a lot of the remaining terms there, they're actually represented with equilibrium equation number 2, and we're left with the following, where the total moment is the negative of the time derivative of rho v, I guess volume, I should say volume since we also have velocity, times r2 plus the time derivative of rho times volume times velocity times r1 minus sigma 2,1 times the volume plus sigma 1,2 times the volume. All right, so now it's time to equate those two equations. We have them as simplified as we can get, so we're going to equate them. So if you guys forget, we're basically saying that the change in the angular momentum with respect to t, that's equal to that summation of the moments. Therefore, we get the nice equation over here. And if we look, we say, well, hold on one second. Things start to cancel. If I look at rho times v times the velocity 1, well, I have that on both sides. I can cancel it. And the same thing goes for the other time derivative term. They cancel. Therefore, we're left with the following equation. Now, if we look at this, sigma 1,2 minus sigma 2,1 times the volume is equal to 0. Now, there's going to be two scenarios that happen. It's either sigma 1,2 minus sigma 2,1 is equal to 0, or a delta V or the volume is equal to 0. Now, of course, we just know, because we want to keep things physically possible, that we're dealing with non-zero volumes. Therefore, delta V is equal to 0 is actually not a feasible option. Therefore, this statement only holds true if sigma 1,2 is equal to sigma 2,1. Now, again, this process was for about the angular momentum about the E3 axis. If we repeat this process for the angular momentum about the E1 and the E2 axis, we derive a very similar conclusion in that sigma 1,3 is equal to sigma 3,1 and sigma 2,3 is equal to sigma 3,2, which in general means that sigma ij is equal to sigma ji, or basically our stress tensor is symmetric. So again, it's a very important thing that we discussed when we talked about the Cauchy stress tensor, and now this is the proof for it. Proof gets really messy. It makes for a great midterm or final question. However, I think it's a little bit mean, so that's why I want to show you guys where exactly this comes from. So for the graduate students or even the higher up undergraduate students, they can stop asking me why or where it comes from. This is where it comes from. Now, one last thing I want to touch upon before we end this lecture is that when we derived this, we assumed no couple stresses. So when we were looking at the faces of our cubes, we assumed there was only stress components. However, in some applications, a lot of them more electrical or magnetic, and also in addition to the stress components, there's also couple moments. So there's moments on our edges of the cube. Now, if we consider those moments, well, then our summation of the moments there is going to change, of course. And if that changes, well, then we actually don't derive the following equation. So if we consider couple stresses, our stress tensor actually may not be symmetric. So when we don't consider couple stresses, which we do in all these civil applications, then our stress tensor is symmetric. But I just wanted to make a little note there that not in every situation our stress tensor will be symmetric. However, for you guys in mechanical or civil, we're good to go. We have it we have it easier than the rest. So just something to be thankful for, I guess. All right, guys, that concludes this lecture. I hope it helped shed some light on angular and linear momentum. I know that they sound gross, but as you guys can see, they're not too bad and they lead to some pretty important conclusions. All right, guys, thank you guys so much for watching this video. I will see you guys in the next lecture.